Hey everybody, Mr. Beckstrom here, and today we're going to be looking at Chapter 2, Section 1. This is working with measurement numbers. So we're going to be looking mainly at significant digits, accuracy, precision. We'll also look at a couple other uh, terms that they use in this section. So let's go ahead and get started. So significant digits. So in order to calculate a lot of measurements, we need to understand what significant digits are. And that's really the amount of measurement used in order to measure some quantity. Um, so we have some rules for those, and the rules might seem a little tricky, a little bit complicated, but once we kind of look at some examples and we see what they're trying to do, sometimes it becomes easier. And one way to look at it is what is the least amount of numbers that were used in order to make this measurement. And then we'll look at some examples in a second. But here's the rules. So the first one is that digits other than 0 are always significant. So if it's not 0, then it's a significant digit. The second rule is there's certain times when zeros are significant. The first is when they appear between two significant digits. If there's a significant digit on either side of that zero is also going to be significant. The next thing is it's significant if it's at the right end of a decimal number. And that means that if you have a number with a decimal point and it becomes to the right of that, all zeros to the right of a decimal point are significant, even the ones at the end. And the last thing is, when the zeros are significant, is when there's an overbar over them. And that's usually going to be done with whole numbers, where they measure out a little bit farther than those non-zero numbers that you see. So if you see an overbar, it's going to be significant. And if there's any zeros between those significant digits, they're also going to be significant. Okay, here's when zeros are not going to be significant. If they're at the right end of a whole number, remember a whole number is one that doesn't have a decimal point. So if it's at any zeros on the right end, they're not going to be significant. So we're not going to count those. And all zeros to the left of a non-zero number are also not going to be significant. So we're not going to count those at all. All right, so let's take a look at some examples. All right, so 1020 has 3 significant digits. The 1 and the 2 are always significant because they're non-zeros. The 0 between the two significant digits is also significant. So that's 3 so far, but the 0 on the right of a whole number is not significant. So we don't count that one, and that's part of our rule 3. I think it's 3A. All right, 50,000. It might look like it has more than one, but it actually has one significant digit. Remember, all zeros on the right side of a whole number, a number without a decimal point, are not significant. So the only significant digit here is the 5. All right, 372.250. You might be tempted to say this has 5 significant digits, but in fact it has 6. And the reason is that all zeros on the right of a decimal point are significant, so we do count that 0 there. So we have 5 non-zeros, which are always significant, and 1 0 to the right of a decimal point, which is also significant. So that's 6. All right. 762.00002. Well, that's going to have 8 significant digits. We have the 4 non-zeros, and since the 2 and this 2 are significant, that means all the zeros in between, rule 2A, they're all significant as well, so that's going to be 8. All right, 50,000, and we notice there's a little bar over the third, or the second 0 from the left. So we're going to go out to that. So this is significant. This 5 is significant. All the zeros in between two significant digits are significant. But the 0 to the right of the rightmost significant digit are not significant. And this is a whole number. That's why. So 1, 2, 3, and 4. So 4 significant digits. A little bit tricky, but that's how it is. All right, and then the last one is 0.0005720. All right, that's going to have 4 significant digits. We never count the zeros to the left of a non-zero number, so all of these zeros don't count. And to the right, we only count them if they're to the right of a decimal place, which it is. So that's 1, 2, 3, and we count that 0. That makes 4. You can look at page 91, and there's a few there you can try on your own, and I also put some on here. So go ahead and try this. Determine the number of significant digits of the following numbers. Try that out and see how you do. Pause it when you unpause it. So here's the solutions. I put all the significant digits in red, and I used the rules that showed which ones were significant and which ones weren't. So take a look at those, see if you have any questions. All right, and we're going to talk about precision. So precision of a measurement number is indicated by the place value of its rightmost significant digit. So here's some common place values here. Remember, you start at the decimal place. To the left of the decimal, you start with the ones place, tens, hundreds, thousands, 10,000s, 100,000s, millions. Basically, you keep adding a 0. Now to the right, it's a little bit different. You don't start with ones, you actually start with tenths. So the first place here is the tenths. Notice the TH at the end, then hundredths, then thousands, then 10,000s, then it would be 100,000s and millions and 10 millions if you were to keep going on and on. So when we're talking about the precision of a number, we look at the rightmost significant digit, and then we look at that place here. So for example, in this number right here, the rightmost significant digit is this 1, and that's in the 10,000th place. So the precision would be 10,000ths. All right, so let's look at a couple of examples. Here we have 10,204. The rightmost significant digit is the 4, and that's in the ones place. We look up here. The first one to the left of the decimal is the ones place. And even though you don't see a decimal there, you assume that there is a decimal there. All right, the next one is 1 million. Now remember, 1 million. Y'all might be a little bit young for that movie, but it was pretty good. All right, so 1 million. Well, we know that all the zeros on the right of a whole number, a number without the decimal place, are not significant. So the rightmost is actually the 1 because there's only one significant digit here, and that's in the millions place. Ones, tens, tens, hundreds, thousands, 10,000s, 100,000s, 1 millions place. All right, and then I have 204.222000. We have to go back to our significant digits and know that all these zeros are significant because they come to on the right side of a decimal point. So this last 0 is the rightmost significant digit. It's in the tenths, hundredths, thousands, 10,000s, 100,000s, 1 millionth or millionths place, and that is our precision. All right, let's look at accuracy. Accuracy is, the number of significant digits that the number contains. So this is pretty close to what we did in the very beginning, where we're just counting the number of significant digits. So look at all of these. This first number, 200,300, has an accuracy of 4 because we don't count these zeros since they're to the right of a whole number. We do count these because they're between two significant digits, so 1, 2, 3, 4. So this has an accuracy of 4. This would have an accuracy of 6, and 1, 2, 3, 4, 5, 6. And that's actually not right. That one should be 7 because we do count zeros to the right of a decimal place. So 1, 2, 3, 4, 5, 6, 7. So an accuracy of 7. This one has an accuracy of 2 because we never count the zeros to the left of a non-zero number, but we count them to the right when it's to the right of a decimal place. So this would be 2. This would be 6 because we count the 5, we count this 0 because that's a bar over. So that's a significant digit, and all zeros between two significant digits are significant. So that's an accuracy of 6. So go ahead and try some on page 93. Tolerance, they talk a little bit about tolerance. This is mainly with machine work, and it gives kind of an allowable measurement that you can use when utilizing certain types of tools. So for example, a machine tool might be given as 3.020 plus or minus 0.002 centimeters. And this means that you take this first number here to find the lower limit of what it will perform. You subtract the 0.002 from this number, and to find the upper limit, you add the 0.002 to this number. So that would give you a range of 3.018 to 3.022. So that would basically be as long as whatever you're using that tool on is between these two measurements. That tool should work. All right, and let's talk a little bit about sums and differences, adding and subtracting, and then we'll look at multiplying and dividing when we're dealing with precision and accuracy. So sums and differences, adding and subtracting, we're going to use precision. So when we add two numbers, we are going to round it to the least precise of our original values. So we have to look at those values. And remember, the least precise is the place furthest to the left. So whichever one is furthest to the left is the least precise. So let's take a look here. So if I have 120 plus 100, I have to look at the precision of these two numbers. Well, this one is precise up until the tens place, and this one is precise up until the hundreds place. So this one is the least precise number because this one goes 3 out from left of the decimal, and this one only goes 2 left from the decimal. So remember, the farther left you go, the least precise it is. So we're going to round our final answer to the least precise original value, which is the hundreds place. So normally that would be 220, but we're rounding it to the hundreds place, so that would be 200. Let's look at another one here where we're going to add these 3 digits. Let's look at the precision of each one of them. So this one is to the tenths place, this is to the hundredths place, and this is also to the hundredths place. So the least precise one, that's the one furthest to the left, would be to the tenths place. So that means our final answer will be rounded to the tenths place. All right, so try some on page 94, 95, see how you do. And the last thing is multiplication and division. So instead of precision, like you would use with adding and subtracting, we're going to use accuracy. So when you divide or multiply multiple numbers, you're going to round the resulting value to the least accurate original number. So we have to look at the accuracy of the original number. So here we have an accuracy of 1 significant digit. Here we have 2. So the final answer will be the least out of those. The least is 1, so we're going to round to 1 significant digit, which would be 9. This next one here, this is 2 significant digits. This one is 4 significant digits, so the least is 2. So this final answer will be rounded to 2 significant digits. Remember, these zeros are not significant because they're to the right of a whole number. All right, so try some of these on page 98 and 99, see how you do. If you have any questions, shoot me an email or give me a call. I look forward to speaking with you soon. Have a great day. Thanks.